Well, hello there. This is Craig Hane, or Dr. Dell, and this video is on the subject of infinitesimals, a cautionary tale. Now, this subject is aimed at young students, high school students that are just beginning their studies of math or involved in the early stages of it, and it's designed to get them to thinking about things that they really need to be aware of in math. And this is something that is a tale that's not very often told to my knowledge. Well, let's start off and define an infinitesimal number. Let's first of all consider that you know what the positive, rational, and real numbers are, okay, on the real number line. And you studied that already, and I assume you know what that is. Well, an infinitesimal number is a number which I'm going to call I, which has the property that it's positive. 0 is less than I, but it's also less than x for any real number x. So it's unlike any number that you can write down. We don't have special names for them, but they exist. And they are also called hyper-real numbers today. Now, our ancestors thought about infinitesimals intuitively, just like they thought about virtually everything in math intuitively. Numbers, geometry, and everything intuitively. And if you haven't watched my video on intuition and rigor, you might want to watch that first. That might be a good one to watch first. Now, any real number can be added to this infinitesimal, and then you'll get a hyperreal number called x plus I. And that will not be equal to x, but it will be what we think of as infinitesimally close to x. And you can sort of draw pictures of it, but they're not real. They're just sort of in your imagination, so to speak, in intuition. Now, this x plus I, as I said, is called a hyperreal number. And if you have a hyperreal number, I'll call it h, then we say that the standard part of h is a real number. It's unique, and it differs from the hyperreal number h by some infinitesimal. So any hyperreal number then has a standard part of it. We'll call it x, and x plus I would be h. Okay? Now that's a very quick definition, an heuristic definition of infinitesimals. Now here's the point. It's really easy to prove a lot of things and understand a lot of things using infinitesimal numbers. And when I say prove, today it can be rigorous, but originally it was just heuristic. Okay, let me give you an example of that we cover in our calculus training. Let I be a positive infinitesimal. We define the slope of a tangent line. Let's say that it's the graph of f of x to be the standard part of f of x plus I minus f of x, that quantity divided by I. And it's the standard part, and that's called the derivative of f. Now, if you've studied calculus, this will all look familiar to you, particularly if you study with me. But this is how our ancestors thought of the slope of a tangent line to a curve. And the curve was the graph of a function f of x. Now, let me give you an example how we might calculate the slope of a tangent line. Let's say the function f of x is equal to x squared, and we want to know its tangent line when x is equal to 3. Well, apply the definition. You take 3 plus I and square it, minus 3 squared, all divided by I, and take the standard part of that. This presumably is a hyperreal number. Well, do a little simple algebra. And if you square this out, you'll get 9, and then this is minus 9. That'll go away. You'll get 6i plus I squared. And so you're going to have, when you do a little simplification, the standard part of 6i plus I squared divided by I. When you divide by I, you end up with 6 plus I, and the standard part of that is just 6. So the answer is 6. That's all there is to it. And if you just, instead of 3, you use x, you'll find that f prime of x equals 2x. Now this is the way you can calculate derivatives of functions, and it turns out to be very easy to do for all the standard functions. So right away, life is becoming easier. Calculus, it turns out, is very, very easy to understand heuristically with you use infinitesimals. Now, by the way, as an sideline, and I talk about this in other videos, Wolfram Alpha is an amazing 21st century tool that also makes calculus and differential equations much, much easier. and it makes STEM math in an order of magnitude to learn. And I talk about that on other videos. In fact, you might want to watch my video that I'm going on Wolfram Alpha. So it's kind of related. I use both infinitesimals and Wolfram Alpha to make calculus much easier, much more understandable, much more useful. Now, calculus was invented by several people. One of them was a guy named Leibniz in Germany. And he's the one I give the credit for calculus the way it exists today. Isaac Newton also invented a different version of it in England, but it didn't catch on. He used it; it was good, but Leibniz had the ideas that we use today, and he had disciples like the Bernoulli clan, and then Euler. Now Euler was a mathematician in the 17. By the way, Leibniz did all this in the late 1600s. In the 1700s, Euler did all sorts of things then with math. He produced tremendous math. In fact, much of the math we use today in STEM was produced by Euler. And he used infinitesimal arguments like the one I used above to prove all sorts of things. If you go back and look at Euler's writings, you'll see all kinds of proofs with infinitesimals in them. In fact, quite frankly, I don't think we'd have had calculus today without infinitesimals. I think they were absolutely critical in the understanding and development of calculus. So now the question, well, what happened to them? You're not going to see an argument like the one I just showed you above in any of the regular calculus books that are used today. Well, here's what happened. In the 1800s, the 19th century, mathematicians decided that we had to make math rigorous. Now, I have a video on rigor versus intuition. You can watch that video first probably. They want to make it rigorous. What that meant was they wanted to invent an axiomatic system and prove theorems about it. And they invented axiomatic systems that would make everything they knew about different geometries and numbers rigorous. And as hard as they tried in the 1800s, they simply could not find an axiomatic system that included infinitesimals. I don't know how hard they tried, but they didn't succeed. Now, mathematicians are like all sapiens. We tend to be heuristic. We tend to be kind of conceited in our efforts. Hubristic, I meant to say. They have hubris. Well, what they did in the mid-1800s, they banned them. They said, okay, we can't figure out an axiomatic system that includes infinitesimals, so therefore they must not have any validity. Let's just get rid of them. And they banned them from mathematics. Incredible that they did, but that was they did. Now, scientists, engineers, and applied mathematicians hated it because they used infinitesimals all the time in their arguments. They were valuable. It was easy to understand things, easy to create models. And so, quite frankly, they ignored the ban. So for over 100 years, in fact, it really goes to this day, scientists and engineers and applied mathematicians used infinitesimals in many of their arguments, even though mathematicians said, no, that's a no, because we've banned them. Because why? Well, we can't make them rigorous. If we can't make them rigorous, you can't use them. Big schism. And I grew up in that era. I mean, I got my Ph.D. in 1966, and so all the time I was growing up, I would ask my teachers in college, for example, well, what about this thing with infinitesimals? Oh, you can't use infinitesimals. They're not in our textbooks. They've been banned. Well, that made the treatment of calculus, if you want to do it rigorous at all, the theoretical treatment, much more difficult. And so I would just tell you, if you're a math teacher and you want to study the history of this, go look at the proof of the chain rule in calculus, one of the most important things in calculus for different derivatives, and look at the proof using limit arguments, epsilon delta arguments, compared to using infinitesimal arguments. If you want to see one with infinitesimal arguments, you go to my tier 5. That's how I do it. Well, what happened was, in a lot of calculus classes, the teachers just ignored the proofs. And then that meant you didn't really understand as good as you should the concepts because you didn't see the proofs, because the proofs are too hard. They didn't elucidate anything. So it really made the teaching of calculus very difficult and much worse than it would have been. By the middle of the 20th century, when I started studying math, virtually all calculus books excluded infinitesimals. And this made calculus, as I just said, much harder to learn, much harder to understand, much harder to learn, much harder to appreciate it. Now, there were some math teachers that had like an engineering background, and they'd sneak them in. They'd use them. They say, don't tell anyone, it's not in the book, but this is how we can look at them. I saw that. I taught at engineering school back in those era, and that's what they would do. They said, well, we don't really care about those. We're not theoretical mathematicians. We're applied mathematicians. We're teaching engineers, so we don't really care about it. There's quite a rift between the math department and the science and engineering departments. It was quite something to see. Talk about tribal belief systems and influences. Well, guess what happened now? Just guess what happened. It's really embarrassing for mathematicians, I think. In the mid-1960s, in fact, the year that I got my Ph.D., and coincidentally, a mathematician came along and was able to invent an axiomatic system called the hyperreal number system, and it included infinitesimals. Notice I said invent. We invent axiomatic systems. Okay? And the ones we invent are the ones we use then. Because the mathematicians 100 years earlier couldn't invent this system, they weren't smart enough, wise enough, lucky enough to invent it, they banned infinitesimal. Now we had one, it worked. Abraham Robinson was the guy's name. Wow. Amazing. I heard about it shortly after I got my Ph.D. and I got my Ph.D. in algebraic number theory. It had nothing to do with what he was working in, but I was studying those kind of things anyway, and it was really interesting. I go, oh my goodness, they're back. Wonderful. Now we can reunite mathematics and science and engineering, and we can now use infinitesimals because now they're rigorous, so we can use them heuristically. Well, it didn't happen. Why not? Well, I don't know. There's a big investment in calculus textbooks and in course syllabi and in the way calculus teachers were taught to teach and so forth. And I'm guessing that was really the reason. They just didn't want to change what they were doing. I mean, all calculus textbooks were essentially obsolete at that point because they were full of this difficult theoretical treatment that was now superseded by a much better theoretical treatment, infinitesimals. In fact, Jerome Kiesler at Wisconsin wrote a calculus textbook that used infinitesimals. And I met Jerome, and this was in, I don't know the year, it was in the early 70s. Great. Well, guess what? No one would adopt it. It's out of print now. I got 2 copies of it sitting on my shelf. All the work he put into it, and no one would use it. Now, that's sad enough, but the sad part is, who suffered? It was the students and the teachers that suffered. Even today, this is 2019, I'm doing this video. Both high schools and many universities are still teaching the now obsolete approach to calculus. This is my opinion, of course, but believe me, I'll be glad to sit down and debate it with any calculus teacher that wants to, or mathematician for that matter, but particularly math educator. Mathematicians, quite frankly, theoretical mathematicians, to be honest about it, don't care about calculus. To them, it's an elementary subject. That's for the scientists and engineers. They're way beyond that. They don't really care. The math educators are the one that control this, and they don't want to change. I mean, when the scientific calculator came out, they didn't want to give up all their books with slide rules, so they had to because it was just so obvious. But for some reason, the thing with infinitesimals hasn't come across. Now, the worst part of all this is when you ignore the infinitesimal theory, the students don't learn the concepts nearly as well as they can. They can learn them so much easier and better with infinitesimals. In Tier 4 and 5, in my program, of course I use infinitesimals. And I'm going to tell you right now, it makes learning calculus, it goes from maybe a 6 or 7 in the difficulty scale down to a 1 or a 2. So in our Tiers 4 and 5, we do use infinitesimals. And I can tell you this makes learning calculus much easier and much better. You learn it so much better. You really understand it better when you can see it and conceptualize it. So this is what we really have to do today, in my opinion, and I hope that other math educators will pick this up and do it. I will be really glad to debate this with any teacher or math educator. Now, people, you can't always win a debate just with logic, but the point is we can demonstrate it. Okay, now, so what's the cautionary tale? I said, what's the cautionary tale? Well, if you go back and watch my video, What is Math? I talk about what is math. It consists of axiomatic systems that we invent. And there's all kinds of potential axiomatic systems out there. Steve Wolfram says, there could be thousands of axiomatic systems. In fact, he says the ones that we've invented as sapiens, where do they rank? And he said they rank about 50,000th. I have no idea how he came up with that, but the point being, you can invent a lot of axiomatic. After all, in the 1800s, the smartest mathematician in the world could not invent an axiomatic system, or did not, that had infinitesimals. And then 100 years later, it was done. So what if you can't find an axiomatic system that satisfies your heuristic and intuitive concepts of the way things are? Well, obviously, mathematicians ban them. And then when they ban them, no one studies them, and that's the end of it. Now the question is, what are we banning today? What are we banning today? Is there an axiomatic system that would give us a much better math model of reality? We learned over 100 years ago that non-Euclidean geometry axiomatic systems gave us much better models than Euclidean geometry. There would be no Einstein relativity theories today with Euclidean geometry. I've talked about that on other videos. You wouldn't have GPS today. That technology depends on Einstein's physical models. They depend on non-Euclidean geometry. So we wouldn't have GPS if we hadn't invented a different math, and that didn't happen until the 1800s. They realized in the 1800s the Euclidean geometry was not unique. There were non-Euclidean geometries, and it turned out those made a better scientific model. Well, here's a question for you. You might have heard of the Planck space-time thing. There's some people that think that possibly our space-time reality, whatever we mean by it, consists of discrete, I'll call them pixels, and that it's not really continuous. Now, our calculus today and differential equations are all based on infinity and continuous functions. Well, maybe that's not what reality is. Maybe it's like a TV with pixels. We can't perceive them. We don't have strong enough microscopes to see them, but that's how it really is. And if you're going to really understand and create a physical model of our world, maybe you need mathematics that's discrete, not continuous. I don't know. I'm just saying, what if? I'm talking to young people here today. Maybe there's some young genius that will spark an intuition and a thought. I'll go beyond that. What if there's a non-physical component of the reality that we live in? I happen to believe there is. William Tiller has models of it and experimental evidence of it. I'm very convinced myself that there's a non-physical component of the world we live in, the reality we live in. It's non-physical. In fact, I believe that's where our memories are probably stored. I certainly believe that's where our spirit is, our soul, and we don't really understand it very well. Tiller has a model. He's even got a math model of it that he says is just a beginning one to look at it. It's a frequency-based model. I won't get into that. I highly recommend William Tiller to you, to go to his website and read some of his white papers, read his books. But do we need new math models to understand this? I suspect that we do. I think our axiomatic system today, which has evolved sort of over time in a sort of a not random way, but somewhat that, I suspect they're inadequate today to create a model that really, really lets us know what life is all about. Another example today, there is a model today that we know about called the complex exceptional Lie group, and it's called E8. And some people say it's the most complicated mathematical structure we've ever invented. It's based on 8-dimensional, 8 hyperspheres, and it has all sorts of internal symmetries. And there are people that believe that we can create a better physics model than our current standard model based on E8. Garrett Lisi being an example, and there's others. Well, I don't know. I have no idea. But here's a question. What if some alien civilization has created some axiomatic system that we have? Well, I say created the same. What if they created a different one? Who knows? I mean, it may be that we can't really understand reality today, especially non-physical reality, with our math. Now, if we had, as I said earlier, if we hadn't created the non-Euclidean geometries, there'd be no GPS today. Don't you all use GPS, Global Positioning System? It's in our smartphones now. It was an exotic technology a few years ago when it first came out, and of course it was developed for the military originally. Now we all have access to it. But there wouldn't be GPS if we didn't. If somebody had not invented non-Euclidean geometry. That's an axiomatic system, and Einstein used it to create his relativity models. And there's two correction factors you have to use to make GPS. One comes from special relativity. One comes from general relativity. Really quite interesting. And you're a high school student. I'm talking to young people now, high school students or people that are just starting to learn math. These are the things that you need to be aware of. There's an awful lot to learn, and the last thing you need to be learning is obsolete axiomatic systems, and particularly obsolete tools. Not the systems are okay, but obsolete tools, and not having the right concepts available. This is all food for thought. This video is food for thought for people that are interested in mathematics and science and engineering and want to grow and explore. I just can't even imagine where I would be today had someone known these things and taught me these things back when I was a young guy. I mean, most of the things I'm telling you about, when I was a high school student, no one I knew had any idea of them. There was no one that I knew, even at DePaul University, where I was in my hometown. I learned math from Dr. Clint Gass at DePaul when I was in high school, and then he sent me to Oberlin. He got me into Oberlin, and I learned a lot more math there, then to Indiana University. Nobody knew a lot of this math then. In fact, nobody knew that infinitesimals could be made rigorous all during that time. I got my Ph.D. the year that they finally published the hyperreal system, and so on and so forth. And then, of course, much has come since then. There's all sorts of things today. I talked in one of my other videos about Fermat's last theorem and what it took to prove that. And it took concepts that were not invented until long after I had my Ph.D., and it was finally achieved in the 1990s when they finally did it. Well, anyway, there's a lot to think about. As you study math, and you want to ask yourself, what are the axiomatic systems that you want to study? What interests you? And boy, believe me, there's lots of them. I mean, there's a huge number of current axiomatic systems. But what new ones might we need to create? Could you create an axiomatic system that let us create a better scientific model to understand phenomena that currently we don't understand? That's what Tiller talks about a lot. And I think that, back in the early 1900s, we didn't understand the black body problem. And we didn't understand that the concept of quantum theory. In fact, when the first ideas of quantum theory came out, everybody thought it was crazy. And now today we have quantum theory based on certain axiomatic math systems, but it's got a lot of mysteries in it, believe me. And it contradicts relativity theory, which is based on different math models. So, in order to unify physics today, my guess will be we're going to need a new math axiomatic system that no one's thought of yet. And I don't know what it is. I'm just a high school teacher. What do I know? Anyway, I hope you enjoyed the video and the other videos. They're made to stimulate your thoughts and to educate you and to make you understand more and more about what math is about and what you can do with it and that sort of thing. So, Dr. Dell, I hope you're having a great life. I'm certainly enjoying mine, and I will maybe see you on another video.